For the last objective of the lab, we're going to try and tie together everything that we've learned so far and also introduce fixturing. So say I have some part here that I would like to perform quality assurance on. In this case, I'm modeling using a small breadboard that has a wire in it so that it has a unique orientation. There's three things that I want to check. I want to see whether it is close to the correct height, close to the correct width, and that the surface is clean, like this control piece. And we know already that we can get measurements, like height and width, using fine segments, so let's try to do that. If we just insert here, we're going to use a region like this, and we want to check the height, all we need to do is create the box, properly orient it. We want a white segment, and we're okay with an angle range of 10 degrees. We can, let's show result graphics only for now. So we insert this here, and we do find an edge, but the problem that we're going to find is now, if I were to move this part, say it's coming along on a conveyor belt, and not every part is perfectly aligned with this control image that we have now. Say it comes in over here. Well, now you'll see that we actually have no idea what the distance is, because we just have not found an edge. And we need to find a way to fixture our sampling window for this find segment function to the part so that it moves with the part after it's been identified. To do this, we can use a function called find patterns. What this does is it looks for certain unique features about the part that are easy to recognize in the future. So if we bring our piece back into the middle here, as I mentioned, we have a unique orientation. This can be used with find patterns for a model region of our choosing, and a search region also of our choosing, with an angle range of up to 180 degrees so that we can rotate it into any orientation we want. I'll show you what this has an effect on in a minute. And we'll show input and result graphics. So what this does is it looks for features on here that give it a unique orientation. In this case, we found this slot. Now, the problem that we're going to have is that if our control piece here has some surface defect, just searching for this may not actually yield the result we want. So what we actually want to do is use the smallest area that we are most certain will always look the same, that is also uniquely oriented. To do this, we could change our model area to just be this bottom slice, since we're fairly certain that most of the surface is not going to be affected, and this has a unique orientation given that we have 3 edges and a demarcation on one internal part. So if we switch to this, and just because I've done this before, I know that rather than an edge model, an area model works better. You can now see that we have a unique fixture down here. And we know that find pattern returns certain values for row, column, and angle. These row and column values are actually the pixel location at which this crosshair is located. So now we can perform operations relative to the location of that crosshair. To give you an idea of what I mean, I'm going to take my edge function here, bring it down here, and instead of using the region like this, selected relative to 0, 0, and 0, what I can do is expand this fixture section, tell it to rely on the row, column, and angle of my find patterns crosshair, and now this region is going to be located relative to these points instead of 0, 0, 0. So my region now is going to be relative to this point here, which means that if I place it here, if I can get it to rotate for me, even when I move the part around in the frame, so long as this pattern is recognized and a crosshair is found, this region will be relative to that. And now I can move it around wherever I like, and I'm still finding the edge. And as mentioned, we have up to 180 degrees in either direction for which patterns can be found. So even as I rotate this around a complete 360 degrees, I'm able to find my edge. And just like in the last exercise with the calibration, if I change my image that I rely on to be the calibrated image, I can convert this into a millimeter reading. I'm using the same 20 millimeter calibrated grid, and so my reading looks to be pretty accurate. To get my other dimension, all I need to do is copy the function over and change my region so that instead of looking for this height dimension, I'm searching for width. Once I have this adjusted, and everything else looks fine to me, you'll see that I'm finding that edge. It's the 0 and 1 lengthwise, and my value comes out here. Now we can use some control logic to make an easy representation of whether our part here is within tolerance. One way to do that would be to say if the absolute value of our measurement minus the reference value is less than 1, that is, it falls within a 1 millimeter tolerance in either direction, we can print pass, and if not, we can print fail. So you see here that because we are 34.1, which is within 1 millimeter of this value, it puts pass. We can do something similar for here, and instead we would reference, what is this, F26, F25, and D16 is fine. This now also passes. The last thing we want to do is check the quality of our surface finish. An easy way to do this that introduces a new concept is to do the compare image function. What this will do is take a control image that we train it to recognize and the current triggered image and compare them. And the differences between the two will be highlighted as white pixels. So when we do this, what we want to choose is our reference image. For now we can use the calibrated image for simplicity. We still want to use a fixture, otherwise we might just be looking at a different part of the screen, and because the part is somewhere else it'll think there's a difference, and that's not actually what we're interested in. We're interested in the part itself. So again, we'll use the row, column, and angle that we found with the find patterns function. And in this case we want to select a region pretty tightly around this item. We leave a little bit of padding so that we can do other searches within that region later on. These options are not very important, and we'll do result graphics. So if I hit OK here, you'll notice that now, because my image that I've triggered is identical to my trained image, there's no difference whatsoever. But if I were to, say, rotate this and maybe cast a shadow over it and trigger a new image, you can see that because there's a change in the lighting condition, this now appears to indicate that there's a difference in the parts that are there. If I take another picture, it darkens significantly, which means it's pretty much the same. One helpful function that we can employ is the point filter, which allows us to do operations on each individual pixel on an image. Now, if we take our control part here, we know that it looks a certain way. If we do a point filter on this image where we've modified this, what we can do is select one of the options. After fixturing our region again to our find patterns function, we can choose to select the options from this menu. Each of these does something different. Binarize will take values that are above a certain threshold and shoot them up to the maximum, as you can see here, and shoot ones below that threshold down to the minimum. So the only pixels that will be shown are completely black and white. Clip takes the range above the maximum threshold value that we set here and sets it all to the threshold itself. So anything above a score of, say, 200 will get knocked down to exactly 200. Likewise here, we remove some from the minimum range, so anything below 60 will now be set to 60. You can see that things change quite a bit there. The one that I like the most is actually stretch, which leaves the middle range of an image intact but amplifies the extremes. So parts that are very different will be modified severely in one direction or the other. So anything of a value below 60 gets moved directly to 0. Anything of a value above 220 would be moved all the way up to 255. So if I insert this, we see that, of course, there's not much of a difference because I'm still referencing the control part, which looks pretty much the same, as you can see from absolutely no difference in the screen. Now, if I take one that has a plausible surface defect, I've just inserted some wires here, you can see that now there is quite a bit of difference. There's also these knobs on the outside because it's a different type of breadboard. And so now my little point filter here amplifies these differences, and I can see which parts are most different. This should make it very clear for, say, a histogram function to be able to tell that there is a significant difference. So if I go ahead and extract histogram on this image, I can see now that there is a decent bright count here. Whereas if I swap back in my control part, my bright count is extremely low, which means that it's pretty much identical. So now we can use control logic on this bright count and set a threshold. If it's above that, what we know is that the part is significantly different from what it should be. So for our control part, say, if I put my part back in here and I just take like a look at some of these values, let's say that if there are more than 300 bright pixels, I want my part to fail. I would go here and go with an if function. If this cell has a value greater than 300, print fail. If not, it passes. So right now it's failing because it is not the correct size. You can see also that our dimensions here are failing. Don't worry about this too much. The calibration is going to affect this quite a bit. And also the fact that the calibration plane, which is a sheet of paper lying pretty far away from the camera, is not going to be at the same height as these breadboards. Makes it difficult for you to get a perfect calibration, but just to get some handle on the theory, we're doing it this way anyway. You can see here that it's also catching the nub. It should fail in that respect. And actually I could have made these catch this and fail as well. For now though, you can see that it is failing the surface test. And if I swap back in our original part, actually I've made a mistake. You need to come in here and first of all, not just choose the image, but also set your fixture. So right there is an example of my fixtured image that I've been using to do the calculations upon is not matching up with reality because this is looking for a different reality than this image is providing. So if I come here and I fix my fixture, and my region as well, just to make sure that it's actually working, I should be able to get the histogram out, and I do. So now I can see that my bright count has shot up significantly, which means that there is a large difference, and of course it should fail. If I swap back in my original part, it falls very low, which means that it passes the surface QA. So this is all that you should need to do. This can be quite a bit more involved, so if you don't finish that, that's probably fine, but do make an effort to get this far. Because once you've done this, the only skill left to master with this camera system, which we will not have time for, is using serial I/O to indicate that it's passed the QA, and then on your conveyor belt, you can communicate with your robotic arm and tell it to bin certain parts that have failed the QA and let the rest that have passed move on. And that's ultimately what you want to do as an automation engineer, because once you've mastered that, now you have fully automated your conveyor belt for both optical QA and for processing the material to figure out if it needs to be used further down the line or rejected to save your company quite a lot of money and possibly prevent damaging lawsuits.